Tonight, we are going to explore the biggest question humanity has ever asked. A question that has haunted philosophers, scientists, and dreamers for thousands of years. A question that, when you truly contemplate it, changes how you see everything. Are we alone in the universe? By the end of this journey, you'll understand exactly where we've looked, what we found, and why the answer, whether yes or no, is equally terrifying. If you enjoy these explorations into the cosmos, a like or a subscribe helps others find these videos. Now, settle in. Let's begin. Before we can meaningfully ask whether we're alone, we need to understand just how vast the cosmic arena truly is. And I want to be honest with you, the numbers we're about to discuss are so large that your brain will actively resist comprehending them. That's normal. Human minds evolved to understand distances we could walk, quantities we could count on our fingers. The universe doesn't care about our cognitive limitations. Let's start with our own star, the Sun. It's a fairly ordinary yellow dwarf star, about 4.6 billion years old, roughly halfway through its expected lifetime. Every second, the Sun converts about 600 million tons of hydrogen into helium through nuclear fusion, releasing energy that travels 93 million miles to warm your face on a summer afternoon. That distance, 93 million miles, is called an astronomical unit. Light covers that distance in about 8 minutes and 20 seconds. When you look at the Sun, you're seeing it as it was 8 minutes ago. In cosmic terms, that's practically instantaneous. Now let's zoom out. Our solar system extends far beyond the familiar planets, past Mars with its rusty deserts, past Jupiter with its great red spot, a storm larger than Earth that has raged for centuries, past Saturn with its magnificent rings, past the ice giants Uranus and Neptune, past Pluto and the other dwarf planets of the Kuiper Belt. At the very edge of our Sun's gravitational influence lies the Oort cloud, a vast spherical shell of icy objects that may extend nearly 2 light-years from the Sun. A light-year is the distance light travels in 1 year, about 5.88 trillion miles. The Oort cloud is so distant that objects there take millions of years to complete a single orbit around our star. And yet, in cosmic terms, our entire solar system is practically nothing, a speck, a mote of dust in a sunbeam. The nearest star to our Sun is Proxima Centauri, a small red dwarf about 4.24 light-years away. If you could somehow travel at the speed of our fastest spacecraft, the Parker Solar Probe, which has reached speeds of about 430,000 miles per hour, it would still take you over 6,000 years to reach Proxima Centauri. Let that sink in. Our nearest stellar neighbor is 6,000 years away at the fastest speeds humanity has ever achieved, and Proxima Centauri is practically next door. Our galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars. We're not entirely sure of the exact number because counting stars in a galaxy is remarkably difficult, especially when you're inside that galaxy looking out. It's like trying to count all the trees in a forest while standing among them. The Milky Way is a barred spiral galaxy, roughly 100,000 light-years in diameter. Our solar system sits in one of the spiral arms, about 26,000 light-years from the galactic center. At that center lurks Sagittarius A, a supermassive black hole with the mass of about 4 million suns. If you could somehow travel at the speed of light, which you can't according to our understanding of physics, it would take you 100,000 years to cross our galaxy, just our galaxy. And here's where things get truly humbling. The Milky Way is just one galaxy among hundreds of billions of galaxies in the observable universe. Some estimates suggest there may be 2 trillion galaxies out there, each containing billions or hundreds of billions of stars. Let's do some rough math. If there are 200 billion galaxies and each galaxy contains an average of 100 billion stars, that gives us approximately 20 sextillion stars in the observable universe. That's a 2 followed by 22 zeros. 20 sextillion stars. And many of those stars have planets. We now know, thanks to missions like NASA's Kepler Space Telescope, that planets are extraordinarily common. On average, every star in our galaxy hosts at least one planet. Some stars have entire systems of planets, like our own Sun, with its 8 planets and numerous dwarf planets. This means there may be more planets in the observable universe than there are grains of sand on every beach on Earth, possibly far more. Now consider this. If even a tiny fraction of those planets are rocky worlds in the habitable zones of their stars, the orbital distance where liquid water could exist on a planet's surface, we're talking about billions upon billions of potentially Earth-like worlds in our galaxy alone. Trillions upon trillions across the observable universe. With numbers like these, how could we possibly be alone? This is what scientists call the Fermi Paradox, and it's named after the physicist Enrico Fermi, who during a lunch conversation in 1950 famously asked, "Where is everybody?" Given the staggering number of stars and planets, given that our Sun is a relatively young star and there are stars billions of years older, given that intelligent life arose on Earth through natural processes that should operate throughout the cosmos, where are the aliens? Why don't we see evidence of their civilizations everywhere we look? This paradox has troubled scientists for decades, and we'll explore the possible answers later in our journey. But first, let's trace the history of humanity's search for life beyond Earth. It's a story of imagination, ingenuity, and occasionally profound disappointment. The question of life beyond Earth is as old as human civilization itself. Ancient peoples looked up at the night sky and wondered about those points of light. Were they gods? Other worlds? Campfires of distant tribes? The ancient Greek philosopher Epicurus, writing around 300 BCE, argued that there must be infinite worlds, some like ours and some different. He reasoned that if atoms are infinite in number and space is infinite in extent, then there must be other arrangements of atoms forming other worlds with other living beings. His follower, Metrodorus of Chios, put it even more directly. To consider the Earth the only populated world in infinite space is as absurd as to assert that in an entire field sown with grain, only one seed will sprout. But these were philosophical speculations, not scientific investigations. For most of human history, the search for extraterrestrial life remained firmly in the realm of imagination. That began to change in the 17th century, when telescopes revolutionized our understanding of the cosmos. When Galileo Galilei turned his primitive telescope toward the moon in 1609, he didn't see a perfect crystalline sphere as ancient philosophers had imagined. He saw mountains and craters, a world with geography not so different from Earth. When he pointed his telescope at Jupiter, he discovered 4 moons orbiting that giant planet. This was revolutionary. It meant Earth wasn't unique in having a moon. Other worlds had satellites too. The cosmos was more complex, more varied, more interesting than anyone had imagined. As telescopes improved over the following centuries, astronomers made increasingly detailed observations of the planets. Mars in particular captured the imagination. Its reddish color had long associated it with war and blood in human mythology, but through telescopes, astronomers could see surface features that seemed to change with the seasons. In 1877, the Italian astronomer Giovanni Schiaparelli observed what he called canali on the Martian surface, channels or grooves that seemed to form a network across the planet. The Italian word canali was mistranslated into English as canals, which implied artificial construction. The American astronomer Percival Lowell became obsessed with these supposed canals. He built an observatory in Flagstaff, Arizona, specifically to study Mars, and spent years mapping what he believed was an intricate network of artificial waterways. Lowell theorized that Mars was a dying world and that an advanced civilization had constructed a planet-wide irrigation system to bring water from the polar ice caps to the arid equatorial regions. Lowell's ideas captured the public imagination. They inspired H.G. Wells to write The War of the Worlds in 1898, depicting a Martian invasion of Earth by beings from a civilization more advanced than our own. The novel terrified and thrilled readers, and established many tropes that persist in science fiction to this day. But Lowell was wrong. The canals didn't exist. They were optical illusions created by the human brain's tendency to connect scattered features into lines and patterns. When better telescopes, and eventually spacecraft, observed Mars up close, they found no canals, no irrigation systems, no evidence of civilization. This pattern, hope followed by disappointment, would repeat itself many times in the search for extraterrestrial life. In the early 20th century, some scientists proposed that Venus might harbor life. Our sister planet is similar in size to Earth and is closer to the Sun, which led some to imagine it as a tropical paradise beneath its thick clouds. Science fiction writers populated Venus with swamps, dinosaurs, and exotic civilizations. Then came the space age. In 1962, NASA's Mariner 2 spacecraft flew past Venus and measured its surface temperature. The result was devastating to hopes of Venusian life. The surface of Venus is about 465 degrees Celsius, hot enough to melt lead. The thick atmosphere creates a runaway greenhouse effect that makes Venus the hottest planet in our solar system, despite not being the closest to the Sun. Venus wasn't a tropical paradise, it was a hellscape. Mars offered more hope, at least initially. When NASA's Mariner 4 spacecraft flew past Mars in 1965, it sent back the first close-up images of another planet. What they showed was disappointing, a cratered, apparently dead world that looked more like the Moon than Earth. There were no canals, no signs of civilization, no obvious evidence of life. But scientists didn't give up on Mars. The Viking missions of 1976 were specifically designed to search for life. 2 landers touched down on the Martian surface and conducted a series of experiments designed to detect biological activity in the soil. The results were ambiguous and controversial. One experiment, the labeled release experiment, gave results that some scientists interpreted as positive evidence for microbial life. Martian soil samples, when exposed to a nutrient solution, released gases in a way that resembled biological activity. But other experiments didn't confirm this finding, and most scientists eventually concluded that the results were probably caused by unusual Martian chemistry rather than life. The Viking results remain debated to this day, with a minority of researchers still arguing that they detected life on Mars in 1976. After Viking, NASA shifted its focus away from direct life detection. The agency adopted a strategy of follow the water, searching for environments where liquid water existed or might have existed in the past. Where there's water, there might be life, or at least the conditions for life. This strategy has been remarkably successful in revealing that Mars was once a very different world. The Mars rovers Sojourner, Spirit, Opportunity, Curiosity, and now Perseverance have found abundant evidence that liquid water once flowed on the Martian surface. Ancient riverbeds, lake deposits, mineral formations that only occur in the presence of water, the evidence is overwhelming. Mars was once warmer and wetter than it is today. It had rivers, lakes, perhaps even an ocean covering much of its northern hemisphere. This wet period lasted for hundreds of millions of years, possibly longer, more than enough time for life to emerge if the conditions were right. Whether life actually did emerge on ancient Mars remains unknown. The Perseverance rover, which landed in 2021, is collecting samples that will eventually be returned to Earth for detailed analysis. Those samples might contain evidence of ancient Martian life, or they might not. We won't know until the samples arrive on Earth, hopefully sometime in the 2030s. While Mars has dominated the search for life in our solar system, other worlds have emerged as intriguing candidates. In 1979, the Voyager 1 spacecraft flew past Jupiter and its moons, sending back images that would reshape our understanding of where life might exist. One of Jupiter's moons, Europa, turned out to be covered in ice, but not just any ice. The surface showed cracks and ridges that suggested the ice was floating on something liquid.
Later observations confirmed that Europa almost certainly has a global ocean of liquid water beneath its icy shell. This ocean may contain more liquid water than all of Earth's oceans combined, and where there's liquid water, there might be life. But how could liquid water exist so far from the Sun? Jupiter orbits about 5 times farther from the Sun than Earth does. At that distance, any water should freeze solid. The answer is tidal heating. As Europa orbits Jupiter, the giant planet's immense gravity flexes and stretches the Moon, generating heat through friction. This heat keeps the interior warm enough to maintain liquid water despite the frigid temperatures of space. This was a revolutionary concept. You don't need to be in a star's habitable zone to have liquid water. Internal heat sources can keep water liquid in the outer reaches of solar systems, potentially far from any star's warmth. Saturn's moon Enceladus provided even more dramatic evidence. In 2005, the Cassini spacecraft observed geysers of water vapor erupting from cracks near Enceladus's south pole. The tiny moon was literally spraying samples of its internal ocean into space. Cassini flew through these plumes multiple times, analyzing their composition. The water contained salts, organic molecules, and molecular hydrogen, all signs consistent with hydrothermal activity on the sea floor. On Earth, hydrothermal vents at the bottom of the ocean support thriving ecosystems that don't depend on sunlight at all. They're powered by chemical energy from the planet's interior. Could similar ecosystems exist in the dark ocean of Enceladus? We don't know yet, but the ingredients seem to be there. Titan, Saturn's largest moon, presents another intriguing possibility, though a strange one. Titan has a thick atmosphere and lakes of liquid hydrocarbons on its surface, not water, but liquid methane and ethane. Some scientists have speculated that exotic forms of life might exist in these alien seas, using chemical reactions we've never imagined. Even Pluto, that frozen world at the edge of our solar system, may have a subsurface ocean of liquid water. The same is true of several other moons and dwarf planets. The outer solar system, once thought to be a frozen wasteland, may be teeming with liquid water environments. The search for life has expanded from Mars to a dozen or more potentially habitable worlds in our own solar system. But the biggest expansion has been beyond our solar system entirely, to the planets orbiting other stars.
For most of human history, we had no idea whether planets existed around other stars. We assumed they did. If our sun had planets, why wouldn't other stars? But assumptions aren't evidence. Detecting exoplanets proved extraordinarily difficult. Stars are bright, planets are dim. A planet orbiting a distant star is like a firefly next to a searchlight, and that searchlight is light years away. The glare of the star overwhelms any light the planet might reflect. Astronomers needed indirect methods. They couldn't see the planets, but maybe they could detect their influence on their parent stars. The first confirmed exoplanet orbiting a sun-like star was discovered in 1995 by Michel Mayor and Didier Queloz. They detected it using the radial velocity method. As a planet orbits a star, its gravity pulls the star in a tiny circle, causing a slight wobble. This wobble shifts the star's light slightly toward the blue when the star moves towards us, and slightly toward the red when it moves away. The planet they discovered, orbiting a star called 51 Pegasi, was nothing like anyone expected. It was a gas giant, roughly half the mass of Jupiter, but it orbited its star in just 4.2 days. That meant it was incredibly close to its star, far closer than Mercury is to our Sun. Astronomers called it a hot Jupiter, and its discovery raised immediate questions. How had such a massive planet ended up so close to its star? Gas giants were supposed to form in the cold outer regions of solar systems, where ices could help build massive planetary cores. Something strange was going on. More exoplanets followed rapidly. Within a few years, dozens were known. Most were hot Jupiters because those were the easiest to detect. Their strong gravitational pull created larger stellar wobbles. But as detection methods improved, smaller planets began appearing in the catalogs. The real revolution came with NASA's Kepler Space Telescope, which launched in 2009. Kepler used the transit method. It watched stars continuously, looking for the tiny dimming that occurs when a planet crosses in front of its star as seen from Earth. The dimming is minuscule. When Earth crosses in front of the Sun as seen from a distant star, it blocks about 0.01% of the Sun's light. Detecting such tiny changes requires extraordinarily precise measurements, but Kepler was up to the task. Over its 9-year mission, Kepler discovered more than 2,600 confirmed exoplanets and thousands of additional candidates. It revealed that planets are everywhere. Almost every star has at least one planet. Multi-planet systems are common. The galaxy is filled with worlds. Among Kepler's discoveries were planets in the habitable zones of their stars, the orbital distance where temperatures might allow liquid water to exist on a planet's surface. Not too hot, not too cold, the Goldilocks zone. One of the most famous is Kepler 452b, discovered in 2015. It orbits a star similar to our Sun, at a distance similar to Earth's orbit. The planet is about 60% larger than Earth, placing it in the category of super-Earths. We don't know if it has an atmosphere or liquid water, but its location suggests it might. Kepler 452b is about 1,400 light-years away. We won't be visiting anytime soon, but its existence proves that Earth-sized planets in habitable zones exist around Sun-like stars. Such worlds aren't rare flukes, they're common features of the galaxy. Even closer to home, the search has yielded tantalizing results. Remember Proxima Centauri, the nearest star to our Sun at 4.24 light-years? In 2016, astronomers confirmed that it hosts a planet called Proxima Centauri b, orbiting in the star's habitable zone. Proxima b is roughly Earth-sized. Its year is only 11 Earth days long because Proxima Centauri is a small, dim red dwarf star, and the habitable zone is very close in. Whether the planet is actually habitable is another question entirely. Red dwarf stars are problematic. They're prone to powerful flares that could strip away a planet's atmosphere. Planets in their habitable zones are likely tidally locked, always showing the same face to their star, creating extreme temperature differences between the day and night sides. And red dwarfs emit more of their light in infrared wavelengths, which affects how planetary atmospheres behave. Still, Proxima b represents the tantalizing possibility that an Earth-sized world exists in our cosmic backyard. Future telescopes may be able to analyze its atmosphere, searching for gases that might indicate life. The James Webb Space Telescope, which launched in December 2021, has already begun studying exoplanet atmospheres. JWST can detect the chemical fingerprints of gases in a planet's atmosphere by analyzing how starlight filters through during transits. What gases would indicate life? We look for biosignatures, chemicals that are produced by living organisms or that exist because life maintains them. On Earth, oxygen makes up about 21% of our atmosphere, but oxygen is highly reactive. Without life constantly replenishing it through photosynthesis, it would disappear within a few million years, combining with rocks and other elements. The presence of abundant oxygen in an atmosphere is a strong indicator of photosynthetic life. Methane is another biosignature. Most of Earth's atmospheric methane comes from living organisms, bacteria, cows, termites, and other life forms. Methane in an oxygen-rich atmosphere is particularly significant because oxygen destroys methane fairly quickly. If both gases coexist in significant quantities, something must be replenishing them, possibly life. Other potential biosignatures include nitrous oxide, certain sulfur compounds, and gases that have no known non-biological source. The challenge is that we don't fully understand all the ways these gases can be produced without life. False positives are possible. The TRAPPIST-1 system, discovered in 2016-2017, offers perhaps the best opportunity to search for biosignatures in the near future.
This tiny red dwarf star, about 40 light-years from Earth, hosts 7 Earth-sized planets, 3 or 4 of which orbit in the habitable zone. 7 worlds packed into a system smaller than Mercury's orbit around our Sun. From the surface of one TRAPPIST-1 planet, other planets would appear as large as the Moon in our sky, perhaps even larger. It's an alien solar system, unlike anything in our own neighborhood. JWST has already observed the TRAPPIST-1 planets and will continue studying them for years. So far, results suggest that some of the inner planets lack thick atmospheres, which might be bad news for habitability. But the outer planets remain mysterious, their secrets waiting to be unveiled. If JWST detects biosignatures in the atmosphere of a TRAPPIST-1 planet or any exoplanet, it would be one of the most profound discoveries in human history. We would know for the first time that life exists beyond Earth. But detecting biosignatures isn't the same as detecting intelligent life. Oxygen in an atmosphere might come from algae or bacteria, organisms no more intelligent than pond scum. The question that truly haunts us is whether other thinking, conscious beings exist out there, beings who, like us, wonder if they're alone.
The search for extraterrestrial intelligence, SETI, took its modern form in 1960 when astronomer Frank Drake pointed a radio telescope at 2 nearby sun-like stars and listened for signals. Drake's reasoning was simple but profound. Radio waves travel at the speed of light and can cross interstellar distances without being absorbed by the dust and gas between stars. If an advanced civilization wanted to communicate across the galaxy, radio would be an obvious choice. And if that civilization was anything like us, they might be broadcasting signals, intentionally or unintentionally, that we could detect. Drake didn't find anything in that first search, which he called Project Ozma after the fictional Queen of Oz. But the idea was planted. Over the following decades, SETI programs grew in sophistication and scope. The most famous SETI signal came in 1977. Jerry Amon, a volunteer researcher working on a SETI project at Ohio State University, was reviewing printouts of data from the Big Ear radio telescope when he spotted something unusual. A strong, narrowband signal that lasted 72 seconds, matching exactly what a signal from an extraterrestrial source should look like. Amon circled the signal on the printout and wrote "Wow" in the margin. The WOW signal, as it became known, remains unexplained to this day. The signal came from somewhere in the constellation Sagittarius. It was strong, narrowband, and on a frequency near the hydrogen line, a frequency that some scientists had predicted would be used for interstellar communication because hydrogen is the most common element in the universe. But the signal never repeated. Despite numerous attempts to detect it again, the Big Ear and other telescopes found nothing. Without confirmation, the WOW signal remains a tantalizing mystery, possibly a message from another civilization, possibly an unknown natural phenomenon, possibly interference from human technology. SETI has faced a fundamental challenge. The galaxy is vast, and we don't know where to look or what to look for. It's like searching for a specific needle in a haystack the size of the Pacific Ocean, when you're not even sure the needle exists or what it looks like. Early SETI programs could only listen to a few radio frequencies at once. Modern systems can monitor millions of channels simultaneously, but even that's a tiny fraction of the radio spectrum. And radio is just one possible communication method. Advanced civilizations might use lasers, gravitational waves, neutrinos, or technologies we haven't invented yet. Some scientists have proposed that we shouldn't just listen, we should transmit, send messages announcing our presence, inviting contact with any civilizations that might receive them. This idea, called active SETI, or METI, messaging to extraterrestrial intelligence, is controversial. Some researchers argue it's irresponsible to broadcast our existence without knowing who might be listening. If hostile civilizations exist, alerting them to our presence could be catastrophic. Others dismiss these concerns. They point out that Earth has been leaking radio signals into space for over a century. Our television broadcasts, radar emissions, and military communications have already announced our presence to any civilization with the technology to detect them. The cat, so to speak, is already out of the bag. The debate continues, but so far, most SETI efforts remain passive, listening rather than broadcasting. In 2015, a major new initiative called Breakthrough Listen launched, funded by Russian billionaire Yuri Milner, with support from Stephen Hawking and Mark Zuckerberg. With 100 million over 10 years, Breakthrough Listen became the most comprehensive SETI program in history. The project uses some of the world's largest radio telescopes to survey 1 million nearby stars, the entire galactic plane of the Milky Way, and 100 nearby galaxies. It's searching for both radio and optical signals, brief flashes of laser light that might be used for interstellar communication. So far, Breakthrough Listen has detected numerous signals of interest, but all have eventually been explained as terrestrial interference or natural phenomena. No confirmed alien signals yet, but the search continues. Beyond radio and optical signals, some researchers have proposed looking for alien technology in other ways. Advanced civilizations might build megastructures, enormous engineering projects visible across interstellar distances. Freeman Dyson proposed that a sufficiently advanced civilization might construct a swarm of solar collectors around their star, capturing most of its energy output. Such a Dyson sphere would be invisible in optical light. The star's light would be blocked, but would glow brightly in infrared as the structure radiated waste heat. Searches for Dyson spheres have found candidates, but none confirmed. Most unusual infrared sources turn out to have natural explanations. Another approach is looking for evidence of alien travel. If civilizations have been exploring the galaxy for millions of years, they might have visited our solar system. Maybe they left probes, artifacts, or other evidence of their passage. Some researchers have proposed searching for alien artifacts on the Moon, where the lack of atmosphere means objects would be preserved almost indefinitely. Others have suggested examining near-Earth asteroids, the Lagrange points where gravity creates stable orbital locations, or even archaeological sites on Earth where an ancient visit might have left traces. So far, no convincing evidence of alien artifacts has been found, but our searches have been limited, and most of the solar system remains unexplored. The most controversial approach is studying UFO reports, now officially called UAP for Unidentified Anomalous Phenomena. For decades, mainstream science dismissed UFO sightings as misidentifications, hoaxes, or delusions. But in recent years, the topic has gained a surprising legitimacy. In 2017, the New York Times revealed that the Pentagon had been running a secret program to investigate military encounters with unexplained aerial phenomena. Pilots reported seeing objects that seemed to defy known physics, accelerating at impossible rates, changing direction instantaneously, operating without visible means of propulsion. Since then, the U.S. government has released official reports acknowledging that some UAP remain genuinely unexplained. NASA has formed a study group to examine the phenomenon. Aerospace scientist and Harvard astronomer Avi Loeb has argued that some UAP might be extraterrestrial probes. Most scientists remain skeptical. The history of UFO claims is littered with hoaxes, misidentifications, and wishful thinking. Extraordinary claims require extraordinary evidence, and blurry videos of unidentified objects don't meet that standard. But the conversation has shifted. The possibility of extraterrestrial visitors, once relegated to tabloids and conspiracy theories, is now discussed in mainstream scientific venues. Whether anything will come of it remains to be seen.
We return now to Fermi's question, where is everybody? Given the vastness of the cosmos, the abundance of potentially habitable planets, and the billions of years available for life to evolve and spread, why don't we see evidence of alien civilizations? Why isn't the galaxy teeming with obviously artificial signals, megastructures, and colonization efforts? This is the Fermi Paradox, and dozens of proposed solutions have been offered. Let's explore some of the most compelling. The first possibility is the simplest. Maybe we are alone. Maybe Earth is the only place in the universe where life has emerged. This seems statistically implausible, given the numbers we discussed earlier, but we don't actually know how likely life is to arise from non-living chemistry. The origin of life, abiogenesis, remains one of science's deepest mysteries. We don't know how it happened on Earth. We don't know if it was a likely event or an incredibly improbable fluke. If the emergence of life requires conditions so specific and rare that it happens only once per galaxy or once per observable universe, then we might truly be alone. This is called the rare Earth hypothesis. Maybe planets like Earth are uncommon. Maybe stable solar systems are rare. Maybe the conditions for complex life, a large moon to stabilize axial tilt, a Jupiter-sized planet to deflect asteroids, a location in the galaxy away from deadly radiation, are so specific that they almost never occur together. If this hypothesis is correct, the silence of the cosmos is explained. There's simply no one else out there to contact us. But most scientists find this explanation unsatisfying. The numbers are just too big. Even if the odds of life arising are 1 in a trillion, there should still be billions of civilizations in the observable universe. Something else must be going on. Another possibility is the Great Filter. This hypothesis suggests that somewhere along the evolutionary path from simple chemistry to galaxy-spanning civilization, there's a barrier that almost no species passes, a filter that eliminates nearly everyone. The scary question is, where is the filter? Is it behind us or ahead of us? If the filter is behind us, we've already passed the hard part. Maybe the origin of life is incredibly rare, but we did it. Maybe the evolution of complex cells is nearly impossible, but we did it. Maybe developing intelligence is a fluke, but we did it. We're the lucky ones who made it through. But if the filter is ahead of us, we're in trouble. Maybe technological civilizations inevitably destroy themselves. Maybe they develop weapons that they can't control. Maybe they exhaust their planet's resources. Maybe they're wiped out by AI, nanotechnology, or some other technology we haven't invented yet. This possibility is darkly suggested by our own history. We've had nuclear weapons for less than 80 years, and we've already come close to destroying ourselves several times. Climate change threatens our civilization. Pandemics remain a constant risk. If every technological species faces these challenges, maybe none survive long enough to colonize the stars. A related hypothesis is that civilizations don't want to be found. Maybe there's a reason to stay silent, a cosmic predator that destroys any civilization that reveals itself. This is sometimes called the dark forest hypothesis, after a science fiction novel by Chinese author Liu Cixin. In a dark forest, every hunter is also prey. If you make noise, something might find you. The rational strategy is to stay hidden and shoot first if you detect anyone else. If this logic applies to civilizations in the galaxy, it would explain the silence. Everyone is hiding, afraid to reveal themselves. This is a chilling thought, but there's little evidence to support it. If predatory civilizations existed and were methodically destroying others, we might expect to see evidence of cosmic warfare, gamma-ray bursts from antimatter weapons, stars mysteriously disappearing, or other signs of destruction. We don't see any of this. Maybe civilizations just aren't interested in expansion. Perhaps as species mature, they turn inward rather than outward. They focus on virtual reality, artificial experiences, or forms of existence we can't imagine. Colonizing the galaxy might seem pointless to a civilization that can create infinite worlds in simulation. Or maybe they transcend physical existence entirely. Some futurists propose that advanced civilizations might upload their consciousness into computers, becoming beings of pure information. Such beings might have no interest in physical space travel or communication with primitive biological species like ourselves. There's also the zoo hypothesis. Maybe we're being watched but deliberately not contacted. An advanced civilization might observe Earth the way we observe wildlife preserves, studying but not interfering.
Perhaps there's a cosmic ethical code against contacting pre-warp civilizations, similar to Star Trek's Prime Directive. This is flattering to our egos, but unfalsifiable. If the aliens are deliberately hiding, we'd have no way to know. Some researchers point out that we might simply not recognize alien signals when we see them. Our SETI programs assume aliens will communicate in ways we can understand: radio waves, optical signals, organized patterns. But an advanced civilization's communications might be completely opaque to us. Imagine a Stone Age tribe trying to intercept Wi-Fi signals. The signals are passing through them constantly, but they have no concept of radio waves and no equipment to detect them. Even if they somehow detected the signals, they'd have no way to understand that they were communications rather than random noise. We might be in the same position. Alien civilizations might be communicating all around us in ways we're too primitive to recognize. Finally, there's the timing problem. The universe is nearly 14 billion years old, but Earth has only been transmitting detectable signals for about a century. Even if 1,000 civilizations have arisen and fallen in our galaxy over its history, the chances of any two overlapping in time and both being technological at the same time might be vanishingly small. Civilizations might be like fireflies, briefly lighting up, then going dark, separated by millions of years, ships passing in the night across cosmic time. None of these explanations is entirely satisfying. The Fermi Paradox remains unresolved, but that's what makes it so compelling and so haunting.
Let's imagine for a moment that we do find them. That tomorrow astronomers announce the detection of an unambiguous alien signal. What happens then? The short answer is, we don't really know. Humanity has never faced anything like this, and predictions are uncertain. But we can speculate based on how we've responded to other paradigm-shifting discoveries. The first reaction would likely be shock, followed quickly by doubt. Many people would refuse to believe it. They'd demand proof, question the methodology, propose alternative explanations. This is healthy scientific skepticism, and it's necessary. False positives would be devastating. A premature announcement that turned out to be wrong would set back SETI research by decades and make the public cynical about future claims. Assuming the discovery holds up to scrutiny, the next question is, what kind of signal is it? If it's just biosignatures in an exoplanet atmosphere, evidence of microbial life, the impact would be profound, but perhaps manageable. We'd know we're not alone in the universe, but we'd also know that the life is primitive and far away. There'd be no immediate practical implications beyond a revolution in biology and philosophy. But if it's an intelligent signal, a radio transmission with clear structure, mathematical patterns, or encoded information, the implications are far more dramatic. First, we'd want to decode it. What are they saying? This could take years or decades, assuming it's even possible. An alien language arising from an alien mind shaped by alien evolution might be completely incomprehensible. We struggle to understand communication between species on our own planet. Understanding beings from another world might be orders of magnitude harder. Even if we can't decode the message, just knowing it exists changes everything. It proves that intelligence can arise elsewhere, that technology is possible on other worlds, that we're not a cosmic fluke. This knowledge alone would reshape philosophy, religion, and our sense of place in the universe. There would be debates about whether to respond. As we discussed earlier, some scientists worry about alerting potentially hostile civilizations to our presence. Others argue that the benefits of contact outweigh the risks. These debates would become intense and political. International cooperation would be essential but challenging. Who speaks for Earth? The United Nations? The country that detected the signal? Some new international body created for the purpose? These questions would need to be answered quickly, and the answers would be contentious. Religious reactions would be varied. Some traditions would embrace the discovery, seeing alien life as evidence of God's creativity and the vastness of creation. Others might struggle to incorporate it into existing theology. Some might reject the discovery entirely as a deception or hoax. Psychologically, the impact on individuals would vary enormously. Some people would find it thrilling, validating their sense of wonder about the cosmos. Others would find it terrifying, shattering their sense of humanity's special status. Depression, anxiety, and existential crisis might become more common. Economically, there might be booms in certain sectors: space exploration, SETI research, communication technology, and busts in others as people reassess their priorities and investments. The discovery might accelerate space development as humans seek to expand beyond Earth, or it might make such efforts seem pointless if aliens already dominate the galaxy. The long-term effects are even harder to predict. If we eventually establish two-way communication, we might receive knowledge that transforms our civilization, new science, new technology, new ways of understanding the universe. Or we might receive warnings about dangers we haven't imagined, or we might receive nothing comprehensible at all. One possibility that scientists have discussed is that alien knowledge might be dangerous. What if they tell us how to build weapons that could destroy planets? What if they share information that destabilizes our society? Some researchers have half-jokingly suggested that we should be careful what we ask for. There's also the possibility that the signal comes from a civilization that no longer exists. Given the distances involved, any signal we received would have been traveling for decades, centuries, or millennia. The civilization that sent it might have died out long ago. We'd be receiving a message from ghosts, proof that intelligence existed once, but perhaps doesn't anymore. This would be bittersweet, confirmation that we're not alone in the universe's history, but possibly alone in its present.
Whether we find them or not, the search itself matters. SETI forces us to think about questions that ordinary life rarely poses. What is intelligence? What is consciousness? What does it mean to be human in a universe that may contain countless other minds? These questions have no easy answers, but asking them enriches us. They connect us to the deepest traditions of human philosophy and wonder, stretching back to those ancient Greeks who looked up at the stars and dared to imagine other worlds. If we're alone, that knowledge would be humbling. We'd bear a tremendous responsibility, the only known intelligence in the cosmos, the only beings capable of understanding the universe, the only minds that can ask why anything exists at all. The universe would have spent 14 billion years evolving stars and galaxies and planets, all to produce one small world where matter woke up and contemplated itself. That's either incredibly depressing or incredibly beautiful, depending on your perspective. If we're not alone, that knowledge would be humbling in a different way. We'd be one of many, perhaps one of billions of intelligent species. We'd have cosmic neighbors, cosmic relatives, beings who might understand things we can't even imagine. Either way, the search reminds us of our connection to the cosmos. We're not separate from the universe, we're part of it. The atoms in your body were forged in stars that died before our sun was born. The carbon in your cells, the oxygen you breathe, the iron in your blood, all of it was created in stellar furnaces billions of years ago. You are quite literally made of stardust. So is everyone you've ever loved, everyone you've ever met, everyone who has ever lived or ever will live. And if life exists elsewhere, they're made of stardust too. Different arrangements of the same cosmic elements, different expressions of the universe knowing itself. As we come to the end of our journey tonight, I want to leave you with this thought. In all the vast cosmos, on a small rocky planet orbiting an ordinary star in the suburbs of an unremarkable galaxy, something extraordinary happened. Matter organized itself into patterns that could wonder about their own existence. Evolution produced beings that could build telescopes and radio receivers and spacecraft to search for others like themselves. We may never find them,
The distances may be too great, the timing too unfavorable, the barriers too insurmountable. We may be alone in ways we can barely comprehend. Or we may find them tomorrow. A signal might arrive that changes everything, proof that the universe is alive with minds, that we have cosmic companions, that the story of intelligence is written across the stars. Either way, we are here. We are conscious. We are searching. And that in itself is miraculous. Rest well tonight, knowing that somewhere above you, radio telescopes are listening to the stars. Spacecraft are examining alien worlds. Scientists are analyzing data, looking for patterns, searching for signs. The greatest question humanity has ever asked remains unanswered, but we're asking it. And maybe, just maybe, someone out there is asking it too. Good night.